As Dr. Shrestha said, my name is Tyler Clifford. That's Tyler Dittmar, Jones Parkia. Special thanks to our faculty mentor, Dr. Wedge Injector. Our project is Scramjet Combustion Lab Development. So as an introduction, as technology advances, the desire to achieve and understand higher supersonic speeds continues to grow. So scramjet engines are built to reach speeds up to 15 times the speed of sound. And this project will allow the future students and faculty at WMU to conduct experiments and learn about supersonic combustion. Here's a figure of a scramjet engine. As you can see, airflow being inlet into a combustion section where fuel is injected into an expansion nozzle, which will propel the aircraft forward. All right, so our objective for this project is to continue the development of the previous group before us, because we are the third team to take on this project. And we are to provide a half-scale 3D printed model of our design, which you guys can see over there. We'll show the camera a little bit later here. And then initialize new design for slowing the airflow at the end of the testing section, which is our dumping chamber. Conduct CFD analysis to ensure parts meet expectations, and provide organized information analysis at a future. So our requirements for this project are a testing runtime of 60 seconds, interchangeable nozzles to reach a series of Mach numbers, interchangeable fuel injector cavities, and the design must be mounted on our trailer to be transported. And so during our development phase, we wanted to pick up where the previous group left off and revise their model to enhance its form. And what we will be discussing with you guys today is the previous group's design, a walkthrough of each component, instrumentation, full assembly, material selection, and cost analysis.
All right, so for the previous design, the previous group focused on the geometry of the settling chamber, the converging divergent nozzles, the testing section, and the fuel injection plates. Due to various issues we found when we were testing for those individual components, we had to redesign them so that we could have them, so that when we put them in the simulation, they would work better and have the results that we wanted. The previous group also included rough concepts of other components like fuel supply, air supply, the dumping chamber, as well as early instrumentation. What they included in the report was very rough, so we had to go through and start to sort of add detail to those components and sort of thing. So for the air supply system, this is something that's still sort of in the rough stages of development. How the air supply system will work is an air compressor and air dryer will take air from the surroundings and put it into the reservoir where it gets compressed. Then a regulator will take air from the reservoir at a specific rate, and then that air will go through a heater where it will be heated to a specific temperature that is more ideal for the combustion that we're looking for. And then once that air is heated, it goes into the settling chamber, and then it goes through the rest of the.
So for the settling chamber, it's the first part after the air supply system. So it will take in the pressurized certain temperature air, and it will standardize the airflow so that the density, pressure, temperature, and velocity will all be constant throughout the end of it. So that testing will be normalized. And then only one settling chamber will be used to settle all different Mach numbers that we have. And we want, for standardized flow, we need a velocity of 3.048 meters a second to 30.48 meters a second. And the minimum radius that we'll need to use is 8 centimeters for Mach 1.5. So after the settling chamber, once it's standardized the flow, we'll go into the converging nozzle, which is this half of it, the first half. And this part is designed to get the subsonic flow to sonic conditions at the throat, and also change the circular settling chamber to a rectangular flow exit, so we can test values easier. And this geometry was determined by Rao's method. And those are all the geometry values that we have for each Mach number. So there'll be 4 different nozzles. And then for the second half of the CD nozzle is the diverging section, which is from here to there. And it's designed to get the sonic conditions at the throat to Mach 1.5 to 2.53. And this was determined by the fundamental method of characteristics of Prandtl-Meyer flow, which has to deal with turning shock waves on a diverging surface to increasing speeds. So the testing section, once we get the flow up to the required Mach number that we want to test it at, we want to keep that specific density, pressure, temperature, and velocity at the starting values. And to do this, we'll need flat surfaces, or else there'll be friction added and we'll lose velocity and pressure. We also want to add a 1.5 degree diffuser to the end of it so that we can reduce normal shock. That would produce back pressure and reduce the velocity in the testing section. And we also need 6 cutouts. 4 of them will be for fuel injection holes, and 2 of them will be for viewing purposes.
All right, so the purpose of the fuel injection plates is to introduce fuel into the airstream for combustion. And the changes that our group made from the previous designs are decreasing the wedge and drop step angles from 30 degrees to 15. And this is to reduce the airflow deflection angle in the testing section, as well as we introduce consistency of injection plugins, which makes it easier for interchangeable parts. So as you can see here, one of our methods is the wedge injector. So 2 wedge injectors will be put together on the left and right side of the testing section. Here's a section view of what you would see. The flow would be one left or right over. So this is the angle here that we changed. It used to be 30 degrees, so it'd be a much higher deflection than what we have now, which is our 15-degree angle. And here is our drop step method. And let me go back to the other slide 1 second. Thank you. You can see here, these are the 2 hole plugins as well, which will lead into the 4 injections into the airstream. All right. The reason I wanted to say that is because there's also 2 holes here on the drop injector, which is what we focused on this semester, making it easier for interchangeable parts. So you can take out the wedge injectors, put in the drop step injector, and plug in the fuel the exact same way. So for the drop step injector, it's going to be on the top or bottom of the testing section. Here in the section view, you can see it's on the bottom. The flow will flow over the drop step, and then fuel will be injected into up the ramp into the airstream.
All right, so for the fuel supply system, we weren't able to get a super developed design fuel system, but the previous group's design used compressed hydrogen gas for their fuel. So the fuel system operated a lot like the air supply system that you saw earlier, where it utilized compression, and by compressing the gas, that once you release the gas through the system into the wind tunnel, it just relied on pressure to move fuel. For our final design, we want the lab to be able to use Jet A fuel, which is a liquid. Liquid cannot be compressed, at least it can't be compressed easily. So we'll have to, the fuel system will have to be redesigned with liquid fuel in mind. This means incorporating a pump into the design instead of just relying on pressure.
All right, so then this is our dumping chamber here, which the purpose of the dumping chamber is to take the speeds from the testing section and slow them down. So we need to avoid creating back pressure into the testing section, which would affect the airflow from the testing section. And our group actually designed 18 total different ways to try to slow down this flow, and 7 of them were dumping chamber design. And our final design was actually inspired by muffler. Here you can see the resemblance between the two.
So the full assembly, when everything's put together, looks like this. This is a full sectional view of the entire assembly. So we have the settling chamber here, the nozzle, the testing section, the dumping chamber. Here's an isometric view of the same assembly. And this picture is not up to date, but this is what the full ensemble will look like when it's equipped with fuel supply, air supply, and set up on the trip. So for instrumentation, for temperature sensing, this wind tunnel is currently planned to house 10 R-type thermocouples. R-type thermocouples have a maximum operating temperature of just under 2,500 Kelvin. They are highly vulnerable to oxidation at above 475 Kelvin. So that is definitely something future design teams will have to consider. It also uses 10 type 6025A high temperature pressure sensors, and those have a max operating temperature between 975 to 1275 Kelvin. They can survive at higher temperatures in shorter, when they're exposed to heat for a shorter amount of time. So if we're just running this for a minute, then we can sort of depend on it to endure the higher heat. And they have a maximum operating pressure of 1450 psi, or to better compare it to our simulations that you'll see in a little bit, it's about the maximum operating pressure is about 10 megapascals. We also researched adding planar laser-induced fluorescence, or PLIF, into the lab. Specifically, we're using what's called OPLIF or OH-PLIF, where we use a laser to excite hydroxide particles produced by combustion. And when the laser excites them, they glow, and then we can use a camera to sort of film that glow and see where the concentrations of those hydroxide species are gathered. And then for the camera, we are taking the previous group's recommendation and using the Phantom TMX 7510 high-speed camera with the Phantom Cinemag 5. That's just like an extra add-on that helps with processing and data collection. Then for material selection, for the settling chamber, the support structures, the converging diverging nozzles, those will all be constructed out of AISI 1060 steel. It has a high amount of strength for a relatively low cost. The testing section will be constructed with...
Yes, and we are working at some point for Kevin's request, and hopefully we get there, for a way that we can provide like an open HTML file.
And the interior will be lined with PC 93104. Wasp alloy is a nickel-based alloy with high heat resistance that's often used in jet engines. DC 93104 is a special elastomer used for heat shielding, insulation, and other aerospace applications. Testing section viewports are going to be made with electrically fused silica. The dumping chamber will also be constructed. We looked at the previous group's broken down cost analysis, and then added in the bigger modifications that we had for this project. So for instrumentation, their original price point was just under $250,000. We added the components we needed for the OH flip setup. So that would be an NDYAG laser, which is about $5,000, an optical parametric oscillator, or OPO, that's about $5,000 as well. For materials, we had to add the cost to build the dumping chamber. We assumed it was roughly 3 times the amount of material used for the testing section, which is about $24,000. No change to the air supply or the miscellaneous assembly components. And then for the fuel supply, we replaced the value there with an estimated $2,000 total for a fuel tank and fuel pump. So the previous total cost for all the parts was about $370,000. And with our additions, the total cost is just about $400,000.
All right, so in the simulation phase, we want to run CFD analysis to ensure quality of parts. Our team used ANSYS to do this. We will be discussing the boundary conditions that we use in ANSYS, the flow simulations for each part, which were at Mach 2.5, except for the dumping chamber, which was done at Mach 3. Combustion analysis, static stability analysis, and heat transfer analysis. All right, so our boundary conditions, you see here, we have like different tables for settling chamber, CD nozzles, testing section, and dumping chamber. Everything used a pressure far field inlet except for the CD nozzles. Pressure far field inlet allows us to insert a Mach number into the inlet of all these different parts, which wasn't necessarily needed for CD nozzles because it created the Mach number. And then everything else uses a pressure outlet.
So for the settling chamber flow, as shown here, there's density, pressure, temperature, velocity, and turbulence. All the values tended to normalize in this design, so the settling chamber was successful. And for the converging diverging nozzles, we wanted to get up to required Mach number, and the density, pressure, and temperature all decreased rapidly across the throat and increased to the required Mach number after the throat. So the nozzles were all working properly. And for the testing section, the density and pressure started to change quite a bit once it got to the diffuser, and the diffuser tended to decrease those. The temperature stayed equal, and the velocity stayed somewhat equal, and there's very minimal turbulence created along the walls. With the drop plate added, the flow simulations had pretty regular results actually for density, pressure, temperature, velocity, and the turbulence. There was very minimal change throughout the entire thing. And the same for the wedge injector. All of them were quite similar, besides the temperature, where it had actually a sharp drop in temperature after the wedge injector was placed, and then it dropped even further after the diffuser. And then for combustion analysis, for the drop plate, there was very low density after the drop plate, and there were shock lines. There were shock lines produced by the drop plate itself, so it created inconsistent results. And the temperature had very high results, high temperatures right after the drop plate, but the velocity stayed similar throughout the entire thing. And then it was quite similar for the wedge injector, where the density was very low, and the shock lines were produced, and the temperature was very high right behind the wedge, and the velocity was somewhat.
All right, for the dumping chamber flow simulation, we also have our table here. There was an inlet of Mach 3 for each simulation. Our idea with that was that the design to slow Mach 3, it can slow the other Mach intervals. And our inlet exit temperature was 300 Kelvin, and we used an ANSYS supersonic solution steering 50 iterations. All right, this is one of our models here. This is the cylindrical dumping chamber. You can see here the third chamber is highly pressurized here. There's a high temperature across the entire 3 chambers. And that high pressure there creates a back pressure here, which is something we don't want because it will affect the testing section flow. And then this is our rectangular dumping chamber design, which also has a very high pressure in the third chamber, temperature is evenly distributed at a high temperature of nearly 825 Kelvin. And then there isn't as much back pressure here, which we don't think will affect the testing section flow. But one thing that will be mentioned in the recommendations here is our Mach number is still about 1.5, so it doesn't effectively slow down completely what we'd like it to be. But that's something the future group will have to redesign and consider.
So with this very, very basic structure that we have designed so far, there was very minimum deformation produced, and will have to be looked at in the future. Some fine tuning just to make the structure look appealing and professional, be advised, and the dumping chamber support has to be added also. For the heat transfer, without cooling, the walls in the outside area come up to be 1100 Kelvin. But if you add just a basic water cooling system, it'll drop the temperature by around 100 Kelvin in the areas with water.
So in conclusion, we updated the settling chamber, the CD nozzle, the testing section, and the injector plate geometry. We added connector plates to the converging diverging nozzles to make them easier to switch out, which was one of the requirements of the build. We added a dumping chamber prototype. We went through several iterations, but it's still got some work that the future teams will have to develop. And we added plans for an OH flip system and documented steps in. We actually documented our simulation process so that the next team won't have to work as hard to figure it out. And the settling chamber CD nozzles testing section shouldn't require much attention from here on out, ideally. And then for recommendations, cooling system, as we went over with the heat transfer analysis, the cooling system would be very useful. We couldn't get around to it this semester, unfortunately. The dumping chamber is not finalized because the air is still at supersonic speeds and we need to be subsonic. And then also using a converging nozzle dumping chamber to scale the size down, and may need to add more viewports into the testing section for the sake of O-flip, high-speed filming, and other visual data. So if it was found that you wanted to put the laser from the O-flip at a different angle, you might need to put an additional viewport to accommodate that. Just something.
Okay, good. So now is the question and answer period, guys. We have one question, time for one question. So anybody have a question for the answers?
I have a question.
Okay, so I will ask one question. What's the most difficult part for your project?
Illegal replacement.
Quick answer.
Mine was definitely the dumping chamber. That's my part.
There's one question.
Mine would definitely be the dumping chamber because I spent probably like 3 or 4 weeks out just trying to complete the flow.
Honestly, for me, research was probably the hardest thing because if you didn't know exactly what you were looking for, it was very hard.
Learning ANSYS Fluent, which is a very rough program.
That was
Someone like heard it. It's it, but I don't know.
Is it any question on the chapter?
No.
Okay, guys, thank you very much. So the next presentation is the closed for the public, so nobody can stay here except those who has, of course, permission from the presenter or the company. Okay.